Okay, so dear students, welcome back. So in our today's lecture, we will be discussing another very important concept, that is the breakdown of Born-Oppenheimer approximation. What does this mean? That there are interactions between our rotations and vibrational levels. So in our last lecture, we have discussed about the vibrational rotational spectrum of a diatomic molecule, and during that discussions we were considered that the vibration and rotational transactions or vibrational and rotational energies are exist quite independently, means there is no interaction between the rotational and vibrations, or I can say the rotations and vibrations of a molecule during their transactions, which we know is Born-Oppenheimer approximation. Further, this Born-Oppenheimer approximation says that the electronic and the nuclear, you can say the nucleus, there is no interaction between the nucleus and the electronic energy level. So, but in the actual case, it is not so. There are interactions between the vibrations and rotations of a molecule. That's why this concept is known as breakdown of Born-Oppenheimer approximation, which means that there are interactions among the rotations and vibrations of a diatomic molecule. So now let's derive an equation for this, and let's see what are the effect of these interactions between the vibrations and rotation. Okay, so far we have assumed that the vibration and rotations proceeds quite independent. So this, what we have so far discussed is this, that these two are proceeds quite independently, means the rotations are not depending on the vibrations, or there is no interaction among the rotations and vibration of the molecule. Now, a molecule can vibrate sometimes about 10 raised power 3 times during a single rotation. So how fast the vibrations are in the molecule? So a molecule can vibrate some around 10 raised power 3 times more during a single rotation. So the time taken by by molecules to undergo a single rotation, in that duration, the molecule will vibrate around 10 raised power 3 times more. So we can say that the molecule vibrate more rapidly as compared to the rotation. So when your molecules vibrate, then there will be change in the bond length of this molecule. So if this is the molecule and this is the equilibrium bond length, or I can represent as REQ. So when the molecules will vibrate or rotate, there will be change in the bond length of this molecule. It can be either stretch or it can be either compress. So means during the vibration, the bond length changes from their equilibrium position. Now, what will happen when your molecule vibrates, and what will happen when the bond length of that molecule changes? We know that the bond length are directly proportional to, are directly related to our moment of inertia, that is I, and another important concept, that is the B, that is your constant, that is usually we know as rotational constant. So these two important factors are depending on the bond length of that molecule. Now, what will happen when there are vibrations and rotation in the molecules? The bond length will change, and due to the change in the bond length of this molecule, these two factors will also change. That means the moment of inertia will change. The rotational constant B will change. So, and we know that we have already discussed some equations that the rotational constant B is equal to h upon 8 pi square IC. And we know that this I, that is the moment of inertia, is equal to mu r square. It means that the moment of inertia is somewhat inversely proportional to our rotational constant B. And again, this moment of inertia is somewhat directly related to this R, that is the bond length of this molecule. It means if there is some bond length change in the bond length taking place, that will also lead to the change in the moment of inertia and the rotational constant of that molecule. Therefore, by taking the value of this I can write this equation as h upon 8 pi square. In place of I can write mu r square c. So here, what I am getting from this equation is that my B is inversely proportional to the r square. It means that if there is any change in the bond length of the molecule, there will also be change in the value of this rotational constant B. Then the relationship between the B and the R is inverse. It means if the bond length increase, the value of B will decrease. So this is the important factor we are going to see from here. However, the rotational constant, this B, depends on 1 upon R square. It means the average value of this quantity is not same as that of, I can say, 1 upon R equilibrium square, where R equilibrium is the equilibrium bond length, which is the actual bond length of that molecule. It means this R equilibrium and R, at the R means the distance at a particular time, which means either your molecule is stretching or compressing. When your molecule is stretching, the R will be greater than R equilibrium. It means the B value at that particular time will be less than the B value at the equilibrium distance. So this is how we are going to see and what are the effects of this change on the spectrum of a molecule. Further, we can say is increase in the vibrational energy is also accompanied by the vibrational amplitude, and hence the value of this B will depend on the vibrational quantum number mu. So the value of B also depends on the value of mu, that is the vibrational quantum number. Means that if you increase the vibrational energy, what will happen? The amount of transaction increases, means the probability of transaction will also increase. It means more and more molecules will go to the upper level. So the vibrational energy is also affecting the value of this B. Now we can have two cases. One case is if the vibration is like simple harmonic oscillator. It means what will happen in case of a simple harmonic oscillator? In case of a simple harmonic oscillator, we usually consider that the bond length will be the same as the equilibrium bond length. So here we consider R square is equal to R equilibrium square, and it will not vary with vibrational energy. So in case if the behavior is of a simple harmonic oscillator type, then simply we can take that the bond length, the change in the bond length we are not considering. However, if the transaction or the vibration is of the n-harmonic oscillator type or AHO, then what will happen with the change in the vibrational energies? The value of B will also change. And here we say, in case of an harmonic oscillator, we have the curve like this, that at a particular distance, the molecule will break down. But for the simple harmonic oscillator, we have a curve of this parabola type, in which we are considering the bond length is very similar to what we have the equilibrium bond length. However, in case of an harmonic oscillator, we have a curve like this, which means that at this particular point, your molecule will break down and dissociate into the respective atoms. So in case of an harmonic oscillator, we are not considering R square equal to R equilibrium square. Means there is the change in the bond length of the molecule during vibration, and an increase in the vibrational energy will lead to an increase the average bond length. So for example, if this is the equilibrium bond length, and if you will increase the vibrational energy, then what will happen? This will lead to the change in the bond length of this molecule. Usually it will increase the bond length of the molecule. So what will happen? If you increase the bond, if the vibrational energy increase the bond length of the molecule, then this will lead to the change in the rotational constant value B. Okay, so we can say the rotational constant B then varies even more with vibrational energy. As you increase the vibrational energy, there are more and more stretching of the bond will take place. And if there is an increase in the bond length, the value of this B will decrease. What will happen this value if the value of this B decreases? So far we have discussed it that the distance between the respective lines are same. However, if the value of B decrease, the gap between these lines will also decrease. So this will affect the spectrum of a molecule. So now let's see. In general, it is plain that since R average usually increases with the vibrational energy. So it means if you increase the vibrational energy, the average bond length will increase, which means if this will increase, the value of B will be smaller. If the value of will be smaller, it means that if we have a number of energy levels, as you increases from V is equal to 0 to V is equal to 1 and V is equal to 2, the value of B will decrease and decrease and decrease as you increase the value of this rotational quantum number. So I can say the B0, B1, B2, the value of B will decrease in this way. So here I have the maximum value of rotational constant in this ground state level, that is B0 is the highest, then B1 and then B2. It means as you increase the vibrational of the molecule, or as you move on to higher vibrational quantum number values or higher energy levels, the value of B will decrease and decrease, and it will lead to the decrease in the gap between the vibrational lines in the spectrum. So for this, we can write an empirical equation. For this behavior, we can write an empirical equation of the type where BV is equal to BE minus alpha V plus 1 by 2. Let's consider this is equation number 1. And this equation will give you a high degree of approximation where your BV is rotational constant. That is, this BV is the rotational constant in any vibrational level V. It can be V0, it can be V1, it can be V2. So the vibrational constant in any vibrational level is equal to BE, where this BE is the equilibrium value. BE is equilibrium value. Which means the BE is the value of the equilibrium, the value of the bond, the molecule at the equilibrium value. It means this is the actual rotational constant of the molecule when there is no disturbance, and it is minus alpha. So it is BE minus alpha. Then what is this alpha? This alpha is a constant, and the value is very small, and positive, and it is different for each molecule. So this alpha is a constant, a small positive constant for each molecule. So the behavior of this B, that is the rotational constant, with the equilibrium, with the vibrational energy can be written as BV is equal to BE minus alpha V plus 1 by 2, where our V is the vibrational quantum number, and the value can be 0, 1, 2, 3, 4, and so on. So this is a simple integer values starting from our 0 and onwards 1, 2, 3, 4, 5, 6. So here we will restrict our discussion only to the fundamental vibrations. So from here onwards, we are restricting our discussion only to the fundamental vibrations. What we mean by this fundamental vibration is that we are only considering the change from V is equal to 0 to V is equal to 1. It means the transaction is taking place from the ground state vibrational level to the first excited state vibrational level. It means that the V1 is the higher energy level and V0 is the ground state energy level. And if we consider B0 is the rotational constant of V is equal to 0 energy level, and B1 is the rotational constant in the V is equal to 1 vibrational energy level, that therefore we can already say that as you increase the value of the vibrational quantum number, the value of this B decreases due to the change in the bond length from the average bond length. Then here we have the case where this B naught will be greater than B1, because as you increase the vibrational energy, the bond length increase. Due to the increase in the bond length, this B decrease, because this B is inversely proportional to square of the distance between the atoms. That is, as you increase the bond length, the value of B decrease, or I can say as you increase the vibrational energy, the bond length increases, due to which the B decreases. So here the rotational constant in the V is equal to 0 state is greater than V is equal to 1 state. So for this transaction, we can write another imperial equation. So for this transaction, that is the transaction from V is equal to 0 to V is equal to 1, the energy change we can be write as delta E is equal to E J dash V is equal to 1 minus EJ double dash V is equal to 0. What is this J dash and J double dash? We have already discussed in our earlier lecture, last lecture. This is the first vibrational state V is equal to 0. And this is the second first excited state where V is equal to 1. What are these J and J dash means? We know that this vibrational energy level is accompanied by a number of rotational energy levels. And this we have considered J double dash is the lower and J dash is the upper rotational energy level. So the transaction, when your molecules are undergoing transaction from one state to another state, this transaction can, the energy of this transaction can be calculated by using this equation. Now we have already the values for this EJ dash V is equal to 1, that will be equal to, we have already derived these values, which is equal to omega naught bar plus B1 J dash plus 1. That is, we have the value of the rotational constant, that rotational energy levels, Bj into J plus 1. Here J dash we are considering for the higher higher energy levels, and we have to subtract this from B0. B1 is for this energy level, and B0 is the rotational constant for our V is equal to 0 energy level. It will be B0 J double dash into J double dash plus 1 centimeter inverse. So let's take this as equation number 2. So we can have an equation of this type from which we can easily derive the energy difference for a, or I can say the energy for a particular transaction. Here again, this omega naught bar, which we have already discussed, is equal to omega E 1 minus 2xe. And usually we have called as the band origin. And this particular omega naught value corresponds to the band origin value. where actually the band originates in a spectrum. And again, from the left side of this origin, we have, so this, if this is the omega naught bar, that is the band origin point, we have values for P branches on the left side, and we have R branches on the right side. So this omega naught is nothing, it is the band origin value. So we have an equation where delta E is equal to omega naught bar plus B1 J dash into J dash plus 1 minus B naught J double dash into J plus 1. Now, if we and apply the selection rules here, we have a selection rule where our delta J can change from +1 to -1. It means our delta J can have either +1 value and it can have our -1 value. And we all know, already know that delta J is equal to +1 for R branches and delta J is equal to -1 for P branches. It means one is going towards the left side of band origin, that is towards lower frequency, and one is towards the right side, that is higher frequency from the band origin. So now here we can have two cases and we can easily apply these two cases to this equation. Now we can have two cases, which means we have delta J is equal to +-1. So let's solve the first case, in which we will take delta J is equal to +1. It means we will solve this equation for our R branches, because for delta J is equal to +1 means it is the R branches which has the higher frequency as compared to our band origin, that is omega naught. And from here, we know that delta J minus delta J double dash is equal to 1. So +1 means it is 1. If I can resolve this equation, the delta J will be equal to J double dash +1. And this will be for your R branches. So now we are solving this equation for the R branches. And now I will put this value in our equation number 2, and I will write it as mu bar R, that is the wave number values for the R branches, is equal to, I can write delta E is equal to omega naught bar. We have already here omega naught bar plus B1. I'm not doing anything with this B1. Now, in place of this J dash +1, I will substitute J dash with this J double dash +1. So what I will have here is J dash, J double dash +1. And in the bracket also I have J dash. In place of J dash, I can write J double dash +1 and 1. It will be your J dash +2. J dash +2. Again, minus P naught J double dash into J double dash +1. So what I have done here is simply I have expanded this equation. Simply what I have done is I have expanded this equation. Now let's try to solve this equation so that we can get an equation for the R branches. Now what I will do here is I will take J dash +1 is common. I have this J dash double dash +1 here, and again I have J double dash +1 here. So what I will do is I will take these as common. So I can again write omega naught bar plus J double dash +1. Okay. What I will remain in the bracket is I will remaining with our B dash B1. Then I have J double dash +2 on this side. And on the left side, I have remaining just B naught minus B0 J double dash. So this is the equation which I got from by solving this equation. So I can further solve this equation is I will write here omega naught bar plus j dash plus 1. So I can put it in a bracket. Now I will open I will multiply this B1 with these two. So I can write here B1 J double dash. And when I will multiply B1 with these two, it will be 2B1. So for this 2B1, I can write B1 plus B1, which is again 1B1 plus 1B1, it will be 2B1. And I have this B0 J double dash. What I will do, I will add here 2B0 term. In this way, one is your B0 minus B0 plus B0. So this minus B and plus B, I will cancel each other and it will not affect much on our equation. So further solving this equation, I can write omega naught bar as such, then J double dash plus 1. Then what I will do is I will try to I will take J double dash as common from these two terms. So I will write here is J double dash B1 minus B0. Okay. Plus I will combine these two terms and I will write here is B1 minus B0, B1 and B0. Then I have here plus B1 plus B0. So what I have done is I have combined these two and I have paired up these two. So now again, what I will do is I will now what I can do is I can take this as common. This is common. So just a minute. So I can further solve this equation is J double dash plus 1. I can write it as such. What I will do is I will take B1 minus B0 and B1 minus B0 is common here. So B1 minus B0, I am taking this as common. What I will remain here is J double dash plus 1. J double dash is said and this side it is 1 plus B1 plus B0. So this is the equation. Now, what I will do is I will multiply this term, that is J double dash plus 1 with this term. So upon further solving, what I will remain here is omega naught bar. So I can write it as plus J double dash plus 1. And I will multiply this with this second term, that is B1 plus B0. So either you can write these terms first or this term first. It will not affect much on our equation. And then plus, if I multiply this J double dash with this term, this whole term, what I will get here is I can write B1 minus B0, that is this one. And if I multiply J double dash plus 1, J double dash plus 1, I will get here is J double dash plus 1 square centimeter inverse. So let me take this as equation number 3. So I can now have an equation for the R branches where our, either I can say mu bar R or delta E is equal to omega naught bar, which is our band origin, our band origin center, plus J double dash plus 1 into B1 plus B0 minus plus B1 minus B0 into J double dash plus 1 whole square. And this is our equation when our when the breakdown of Born-Oppenheimer approximation occurs, and this is the equation for our R branches. So similarly, we can also solve for P branches. Now we have case number second. So now we have case number second, in which we can consider delta J is equal to -1. So delta J is equal to -1 means now we are considering for our P branches. Now we are considering for our P branches, which means we have the branches which have less frequency as compared to our band origin. And we know this equation that J dash minus J double dash is equal to -1. It means the transaction from our upper energy level minus lower rotational energy is equal to -1. And from this equation, I can write J double dash is equal to J dash plus 1. Now, what I will do, I am substituting this equation in equation number 2, which is again, now this is for P branches. What I will write, mu bar P is equal to delta E omega naught bar plus, what I'm writing here is, in place of J double dash, I will write here is B1. The equation is like this: B1 B1 J dash plus 1 minus B naught. So in place of J double dash, I will write J dash plus 1. And again, in the bracket, I have J double dash plus 1. Then that means I will write J dash plus 1 plus 1. That is J dash plus 2. So let me further simplify this equation. So it can be simplified as B1 J dash plus 1 minus B naught J dash plus 1 into J dash plus 2. So this is the further simplified equation. Again, here I will take J dash plus 1 as common, which will result in an equation which is omega naught bar plus J dash plus 1. What I will remain here is this B dash J dash minus B naught J dash plus 2. So this is the equation. Now, upon further solving this equation, let me open this bracket. I can write it as omega naught bar plus J dash plus 1, then B1 J dash minus B naught into this J dash is B naught J dash plus 1, B naught into 2. It is 2B. What I can write here is 2B is, this is minus plus minus. So I can write this is B naught plus B naught. Then again, I will write here is minus B1 plus B1. So this again, B1 and B1 will cancel each other. So it will not affect much on our result or on our equation. So plus. So upon further solving this equation, it will be omega bar naught. What I will do here is I will take this J dash as common from these two terms. So it will be J dash plus 1 J dash. It will be B1 minus B naught. And I will again pair of these two. So I can write here is B1 minus B naught minus B1 plus B naught. So again, let me take this B1 minus B naught is common. So I can write this equation as J dash plus 1. Then I have B1 minus B naught. So here it is J dash plus 1 minus B1 plus B naught. Let me again multiply this term with these two terms. So it will result me omega naught bar. First, I will multiply the second term with this. So it will be minus B1 plus B naught J dash plus 1. And again, if you multiply this term with this, it will be your B1 minus B naught into J dash plus 1 whole square centimeter inverse. And this is our equation number 4. And this is the equation for our mu bar P, or I can say delta E, or the pre-branches when your delta J is equal to -1. So again, now I have here an equation which will solve the P branches. That is the this is the equation for the P branches of the spectrum, or we can say the branches which have lower frequency as compared to our band origin, that is omega naught. In both the equation number 3 and equation number 4, the value of delta J will be 0, 1, 2, 3, 4, 5, and 6, and so on. So the delta J delta J dash can have values starting from 0, 1, 2, 3, 4, 5. Now, here we have used two new terms. One is our mu bar P, and the another one is mu bar R. So these two represents the wave number of P branches and wave number of R branches. P branches means where your delta J is equal to -1, which is lower frequency, and R branches means delta J is equal to +1, having higher frequency as compared to our omega naught bar. That is our band origin. So we can calculate, we can easily determine both P branches and R branches by using this equation. Now, if we combine equation number 3 and equation number 4, we will get a net equation for our mu P comma R. Now, if you combine both the equation 3 and equation 4, you will get a new equation which can be applicable for both P and R branches. So if you will combine, or if you sum up these two equations, you will get a new equation which is equal to omega naught bar plus B1 plus B0 M minus B1 minus B0 M square centimeter inverse. So let's take this as equation number 5. Now we have a new equation which can be applicable for both P and R branches, and this is equal to omega naught bar, which is our band origin center, plus B1 plus B2. This is the rotational constant for higher energy level, and this is the rotational constant for lower energy level. And we have a new term here is M, which have already used in our earlier lecture also. And this M can have either positive value and negative value depending upon the value of whether it is for R branches and P branches, minus B1 minus B naught M square. So here, where this M is positive, and when it is positive, it refers to R branches. And when your M is negative value, it refers to your P branches. So Now we have a net equation, which is the equation applicable to the breakdown of Born-Oppenheimer approximation. It means both rotational and vibrations affect each other. So now this equation number 5 allows us to fit the observed transactions to a quadratic equation from which we can determine various terms, like we have M, we have B1, we have B2, and we can easily calculate all these terms by using this equation and by using the frequencies, frequency of transaction from the spectrum. Now here we know that B1 is less than B0. It means this the internuclear separation is higher and higher in higher vibrational state. It means if you move from V0 to V1, V1 to V2, it means the internuclear distances increases. What it means that as you move on to higher and higher energy level, internuclear distances increases. What will affect this? It means the spacing in the R branches decreases. So what will the result of this increase? The spacing in the R branches decreases. R branches decreases with increasing J values. So as you increase the value of J from 0 to 1 to 2 to 3, 3, and 4, 4, the spacing between the R branches decreases, and the opposite is observed in the P branches. So the opposite is observed in the P branches. It means the spacing between the P branches increase while the spacing between the R branches increase. What this infers? So this will give a distinctive shape to the spectrum. Now let's see why the spacing between R branches decrease and why the spacing between P branches decrease. So here we know that for the R branches, the M is positive. M is positive. And for the P branches, M is negative. So if we substitute the value of this positive and negative here, is what will happen here is this, that if this M is negative and again this M square is negative, again here we know that this B0 is negative term. So as you increase the value of this B, this term will also increases. So the negative term increases means that the separation between the lines, that the lines in the spectrum will decreases slightly. However, here we see that if you substitute the values for the P branches, that is when M is -2, it will not much affect. It will cancel this negative term and the spacing between the P branches increases. Now, if this is the original spectrum of your, that is P, this side we have R0, then R1, R2, then we have R3, R4, so on. And here he said it's P0, P1, P2, P3, and P4, on so on. So the effect of this will be that the spacing between the R branches decrease. So if the spacing, the lines becomes more and more nearer, means R0, R1, R2, R3, R4, and again on the left side the spacing between the P branches will increase. So this is P0, P1, P2, P3. So this is the net result of your breakdown of Born-Oppenheimer approximation. So what we can easily differentiate it from the spectrum, if the line is decreasing on the right side, that is R branches decreases, and if the line on the left side increases, this is the actual spectrum which we can get for a molecule when there is a breakdown of Born-Oppenheimer approximation. So that's all about the breakdown of Born-Oppenheimer approximation and the effect of this approximation on the spectrum of a molecule. So that's all for today. Thank you.